Let's go, maximum parsimony. So, step one in the process is that the computer is going to identify informative sites. And that kind of means what you think, and it kind of means something a little different. So, step one, if a site is constant, it's not informative. So if it's always the same amino acid, like see all of these are F in this column, and all these are H, those are not informative. And so therefore, basically they help us to make sure that we're aligning everything else. They're like little fence posts, but we want to see what's in between the fence posts. We want to look for the differences, because the differences give us the distances, and the distances give us the tree, and the shortest, most parsimonious tree is going to be the best one. Yeah, like some kind of maniacal bonsai gardener. That's how we're going to do things around here in maximum parsimony analysis. But there's another condition. So let's say we have a position. So imagine instead of being a mix of different ones like E and D and A, imagine these are all A, but then half of them are a gap. A gap is not a difference of amino acid, and so you can't use it. And so in this case, it's A and gap, which is the same as if it was all A, which means it's uninformative. What if it was A and X and gap? So X is going to be our unknown amino acid code. And how are we going to get an X in there? Well, if you can read the nucleotides, but one of the nucleotides as you're reading it, it looks like it has two peaks that are about the same. Then you would say that's an N, or that's, one of these combinations. In that case, most of the time, you can't tell which amino acid it actually codes for. And so even if you have 2 out of the 3 nucleotides, sometimes you won't be able to tell what amino acid it's going to make. And so the only sensible thing to do is to say, put an X in there. Better luck next time. And so if we have a combination of A and X and gap, X is not data. It's like the absence of data. It's a thing that's a placeholder that you basically ignore in the analysis. And a gap is not data. It's basically a thing that you ignore. So you can only compare things that are there, basically. And so you have to have at least 2 taxa having each state. So you got 2 of this thing, 2 of the other thing. Otherwise, it's not going to be very useful. And so right here you see that, oh, wow, if I'm trying to make a maximum parsimony analysis with only 2 sequences, that's not going to work. 4 sequences, it's not going to work unless 2 of them are identical and the other 2 are identical, and then all you can do is basically connect those up. And that's not very interesting. This analysis is going to be much better and much more likely to work successfully if you have lots and lots of sequences in there. And so in general, bigger trees with more data and better data are very preferable to smaller trees with less data and fewer species. Or rather, operational taxonomic units. Just because 2 things have different sequences doesn't mean that a taxonomist would say that they are from a different species. For example, you have different sequences somewhere buried in your DNA compared to your brothers or sisters or mom or dad, and you're not a different species from them. We would say that those are just differences and you're within the same species, but that's a different consideration altogether. That's taxonomy. We're not doing taxonomy here. There is an arbitrary element to taxonomy because you have to decide when are we far enough distant that I'm going to call it a new species or a new genus, a new family, subfamily, whatever. And people come with different solutions that make sense based on different criteria, and none of that is our concern right here. So here we go. Step 2. After you've removed the uninformative sites and identified the informative sites that have enough data density and have a suitable amount of diversity in there, then you construct trees. Just sort of randomly construct a whole bunch of trees. And every tree is going to be assigned a cost, and the cost is going to be the total branch lengths. And so we're going to seek out the tree that has the lowest total. So we're just going to make a bunch of trees via various methods, and we're going to take the shortest tree out of the entire bunch. Again, like maniacal bonsai tree farmers, that's going to be our job. That's what we're going to do. So shortest branch length. Yeah, it's the way to go with maximum parsimony. When you have small numbers of taxa, they can actually make every possible tree that connects all those taxa, which is pretty cool. When you have more taxa, then it's going to use different algorithms depending on how we're implementing this. And you can't really be more specific than that because there are different ways. But for example, you could take, if you group things up and said each group of species is, we'll call it a genus, a pretend genus, we could just take one sequence from each genus and then see how those can be constructed. That would be the idea behind this heuristic search. But a heuristic is some method you have of simplifying the data. And the method is going to be better or worse, and it'll be a thing that we can argue about. But for the purpose of this class, that is not the level of detail we need to get into to understand these. So there you go. So yeah, you make your trees. Then you pick the number of, basically genetic distance, number of total branch lengths, and you select the one with the shortest number of total branch lengths in the tree or trees. And there you go. Or you select the 100 trees that have the shortest branch length and you take an average of that. That's like bootstrapping, using the data in slightly different ways. You're coming up with the best trees. You're saying of the best 100 trees with the shortest length, was this branch represented 98% of the time? Then you give it a 0.98 confidence value. Yeah. So those numbers are going to mean slightly different things. You're always going to have to look at the methods section, or they should tell you in the figure legend, to see what the numbers on the nodes mean. But they're always some kind of confidence measure, and they will be different depending on which type of mathematics was used to make the tree in the first place. Okay, so maximum parsimony. So we're assuming we have these sequences, which are really tiny, and just like a 4 amino acid sequence. Great. Let's say we could make these connect together in a tree. There's a bunch of different ways. If you were better at math, or if I was better at math, I could tell you exactly how many for a sequence with 4 different points and 5 different sequences. And anyway, you could connect these all up and say, okay, what's the total cost in terms of branch length and number of changes you need to make these go together? So LKGH is the same as LKGH, and so we can say those actually have a 0 length. We're showing it here just to show that they're related, like in a cladogram. But if this was a phylogram, that branch would have a length of 0, which it should have, yeah, because that's fine. And then we're assuming that at this stage of evolution, there was also the sequence LKGH. But here we have an LKSH, so how many changes do we need to get there? The answer is 1. We have to change S to a G. So great, so that adds 1 to it. Over on this side, before we get to this one, let's say we have the MLGF and the THSF. I'm like, okay, great. So we could just say, well, what if MLGF was the ancestral sequence? Well, we'd have to change 3 things, because really only the F is common between the two. And it doesn't matter if we change 3 on this branch or 3 on this branch, because the total distance between them is the same. And some algorithms will put the distance as sort of half on this branch, half on that one. There's different ways of doing it. And so little differences like that, I would say, treat with a grain of salt, for sure. But anyway, so we've reconstructed MLGF arbitrarily at this one. So great. So how many changes to MLHF? Okay, there's 1. Awesome. And for LKGH to MLHF, well, we would have to change all 4 things. And so our total is 4 plus 1 plus 1. So we're at 6 plus 3 is 9. Total cost is 9. Compare that to this tree. We're actually connecting the same things with the same topology. Yeah. LKGH, we've got 0 branches, LKSH 1, so that part's the same. That part of the tree is the same. But then if we assume that the ancestral sequence is more like this, so it's LK, G, and then F, and then we can say, okay, if it was MLGF, then yeah, there's only the G and the F are going to be constant. So there's only going to be 2 changes you need to get from here to there. And so basically the total is 1 plus 2 is 3, 4, 5, 6, 7. Total cost is 7. Maximum parsimony analysis. Which of these two is cheaper? Total cost of 7. Shorter tree, cheaper tree. That's the tree we want. That's maximum parsimony. So, yeah. It's like maximum parsimony is basically trying to figure out what's the minimum evolution. But minimum evolution methods were doing it mathematically and based on characters. And maximum parsimony is doing it with amino acids or nucleotides based on a tree. Yeah. So, yeah, they're similar in what they're trying to do and kind of similar in the way that they're doing it. But you will get specific differences between them. It's just that I can't tell you what those differences will be for your tree. You would have to look at it and say, oh, okay, this is what it reconstructed differently. Yeah, that's why we do assignments like Assignment 5, where you compare different trees from different methods. So, the tree with fewer changes is the tree we want. Great. What's the problem with these? Long branch attraction. The cheapest way to build the shortest tree is, instead of trying to connect up the long branches with other long branches to your longest node, just to connect those things up right to the root and just say, I don't know how they got here, but this is the shortest tree we can make out of them. Long branch attraction is an artifact, and it is a thing that definitely happens. Parsimony approaches are very susceptible to long branch attraction. And so if we're noticing that all our long branches are connecting up together right at what appears to be the root, then we got to be a little suspicious, and we got to say, maybe there's a little long branch attraction going on in here. And so there are different methods that can sometimes do a better job. Like Bayesian methods will sometimes avoid long branch attraction because they're not just trying to make the shortest tree or the shortest distance between 2 points. They're trying to actually simulate an evolutionary path with some randomness and then do that so many times that they can then take the average of that or sample it at different points and say, here, yeah, this is the most likely tree because when I do this at random, this is the branch pattern that keeps coming back. This is the topology that is common between the trees. So yeah, parsimony algorithms also assume that all taxa evolve at the same rate and that all characters contribute the same amount of information. Like there are no important or unimportant amino acids. Yeah, very egalitarian in that way. Admirable, really, right? Yeah, but not necessarily the best way because, like in an enzyme, the active site is usually 2 or 3 amino acids that are held very close in just the right orientation. The rest of the protein is literally there just to get those into the right orientation. You can change any part of the rest of the protein, and people have and evolution has, and as long as it doesn't affect how those 3 actually join, it is a tolerated substitution of no real consequence. So, yeah, there are definitely parts that are more important, because if you make those changes on the outside of an enzyme, it probably doesn't do anything to it. If you change one of those 3 or something next to it that actually, points it in a different direction, that has a profound change on it because you will make a broken enzyme that will not work. So basically, that's why I'm saying that parsimony, while quick and while admirable in its goals, may not be the best thing for us to use all the time. It's good, and it's a good way of getting to an approximate answer, but there are problems with every single one of these methods. And you have to decide what sort of problems you're willing to live with. Even Bayesian has its own problems, definitely. So based on what you can live with or what you think is making the smallest contribution, that's why phylogeneticists, bioinformaticians will have arguments about these things. So I'm giving you a perspective, but it is not the only perspective for sure on this. But yeah, you got to watch out for long branch attraction. My goodness, it is an artifact and it is bad, and it will skew the heck out of your tree, all in the name of getting a smaller sum of branch lengths, better parsimony score. Okay. So imagine taxon 2 evolves rapidly, so it'll have more changes in its little evolutionary path. Imagine they join up at like the dawn of life, whatever that is, and they've been diverging since. The one will be on a long branch, the other two will be on short branches. So the long branch is going to be the more distantly related one. And so we're going to call that an out group. An out group kind of joins on to the main group. And the position where the out group joins can often be used to estimate like where the root is. Like if you take a bunch of human genes and then you put a chimpanzee gene in there. The chimpanzee gene should join the human genes roughly at the position where chimpanzees and humans diverged X number of million years ago, like 8 million or something like that. Maybe it's 4 million. I forget. Yeah. So anytime two long branches are present, they may be attracted. That is true, and you got to watch for this long branch attraction. So, yeah. If number 2 definitely just does evolve more quickly than the other taxa, it will have a longer branch. But if that's the true tree, the maximum parsimony version of this will actually move 2 out of this group, even though it should be closer to 3, and it'll put it up there. It's hard to tell sometimes, but if there's a situation where you actually know, where you're doing experimental evolution, for example, or where you've got other criteria that you can look at, like development, like geographic position, like position in the fossil record or something, then you may have a reason to favor one tree over another. So yeah. So in this case, the long branch, number 2, is going to be attracted to the outgroup branch right here. And so that's why it's going to move out of the position where it should be and up to here. That's long branch attraction. Our long branches are both going to end up on this side of the tree instead of being where they belong. Yeah. All right. So there you go. That's the end of the maximum parsimony one.